This is Geometry Unit 12, Lesson 2 on tangents and chords. Tangents and chords are different lines that can be drawn in a circle. Let's start with the tangent. A tangent to a circle is a line that intersects a circle in one point. So if I look at my circle O that I have drawn over here, which one of these lines intersects the circle in one point? Well, that would be line T, this one right here. It intersects it at point A. So line T is tangent to the circle at point A. So that is a tangent line. A secant to a circle is a line that intersects a circle in 2 points. It goes through the circle and hits the circle in 2 points. So we said this one is a tangent line. Which one of these would be a secant? It would be line S. Line S is a secant to the circle. It goes through the circle. Notice there's arrows on the end. It keeps going. It intersects it at both points B and C. Okay, now when a secant goes through a circle, it creates what's called a chord. A chord of a circle is a line segment whose endpoints are on the circle. So when the secant line S goes through here, it creates chord BC. So BC, it's a line segment, is the chord of the circle. So you can see on here that the tangent and the secant go through the circle, and the chord is created by 2 points on the circle and is a line segment. Notice that line L right here is not on the circle at all. So that one is not a tangent or a secant, or a chord for that matter. Now let's look at some theorems that deal with tangents and chords. Our first theorem is a tangent and the radius it intersects are perpendicular. So if you have a tangent line that touches a radius, so we have tangent line TAM, it touches the circle at A, and it touches the radius OA right here, that means that the radius OA is perpendicular to the tangent line TN at the point of tangency. So right here, they're perpendicular. So that means that that's a right angle, OAT is a right angle, and OAN are right angles, because they are perpendicular at the point of tangency. So those are right angles. Okay. All right, so that's a very important theorem because any tangent and radius are perpendicular to each other at the point of tangency. A tangent segment is a line segment from the point of tangency to another point on the tangent line. So if you have a line segment at a point of tangency to another point on the tangent line, right there, that is called a tangent segment. So if you have two tangent segments drawn to a circle from the same external point, so if I take my point P here, and that's an external point, and I draw a point of tangency A here, that's a tangent segment. If I draw another segment from P to B, this is another point of tangency, those two segments are congruent. They're the same distance from each other, or from the point of tangency, actually. So that means in the diagram at right, PA is x over 3, and PB is x plus 48 over x plus 3. Since they are drawn from the same external point to a point of tangency on the circle, A and B, PA is equal to PB. So that means this is x over 3, this is x plus 48 over x plus 3. Because they're drawn from the same point to a tangent to the circle, they are equal. So that means that PA is equal to PB. So setting up my equation, x over 3 is equal to x plus 48 over x plus 3. All right, cross multiply. We have x times x plus 3 is equal to 3 times x plus 48. That gives me x squared plus 3x is equal to 3x plus 144. Subtract the 3x, we get x squared is equal to 144. So if we take the square root of both sides, that means that x is going to equal 12. So now that we know that x equals 12, we can now know that the length of PA would be 4. And if we did this correctly, 12 plus 48 is 60, divided by 12 plus 3 is 15, 60 divided by 15 is also 4. They are equal in length. All right, now suppose I wanted to find the length of OP. So if I drew from the center to the external point P right there, I have created OP. There is OP. All right, now, remember that a tangent line and a radius are perpendicular, correct? Yeah, we did that. That was the previous theorem. Now, we know the radius from back here, the radius of our circle, O, is 2. And you can draw a radius anywhere you want. So I'm going to draw from O to A my radius. And that's going to be 2. What kind of triangle does that create? It actually creates a right triangle because this would be perpendicular at the point of tangency. This is a tangent line, this is a radius. Now, if we did OB down here, it would be the same thing. This would be the tangent line, this would be the radius. So it's perpendicular right there. So how could we find the length of OP? How can we find this value right here? Well, why don't we use the Pythagorean Theorem? All right, that would be the hypotenuse of the triangle formed. So this would be AP squared plus OA squared is equal to OP squared. AP we just found was 4. OA is 2. And we're looking for OP squared. Or just we're looking for OP, but we'll find it. So this is 16 plus 4 is 20 equals OP squared. So that means that OP is equal to the square root of 20. Now, if you simplified that, it would be 4 times 5, which is 2 times the square root of 5. So you should be able to recognize both of these. So the length of OP is the square root of 20. So when you have a tangent drawn to a radius, it's perpendicular, and any tangents drawn from an external point, the same external point, are congruent. So those are our theorems about tangent lines. Now let's look at some theorems about chords. Remember, a chord is a segment that is drawn where both endpoints are on the circle. So if a radius or diameter is perpendicular to a chord, then something happens. So OR is my radius, and AB is my chord. All right? So if OR is a radius and AB is a chord, and if they're perpendicular, two things happen. The radius will bisect the chord and also bisect the arc the chord intersects. So when this radius goes through the chord perpendicular, if OR is perpendicular to AB at M, then two things happen. It bisects the chord. So that means that AM will be congruent to MB. This will be congruent to this because the radius will bisect the chord. And also, it bisects the arc that the chord intersects. So if we have our chord here, that intersects arc AB right there. And if the radius is perpendicular to the chord, it is also going to bisect the arc that it intersects. So that means that arc AR, will be congruent to arc RB. So a radius that is perpendicular to chord bisects the chord and also the arc that the chord intersects. All right, one more theorem. If two chords of a circle are equidistant from the center, then they are congruent. Okay, so if I have chord AB and DC here that are the same distance from the center of the circle, notice the distance from O to M and O to N are congruent. That means that they are the same distance away from the center, they are congruent to each other. So because they're the same distance away, they cut off the same amount of the circle. So AB will be congruent to CD. All right, so, arc AB, not chord AB, or chord AB, not arc AB. AB will be congruent to CD. Now, also, if AB is congruent to CD, conversely, if AB is congruent to CD, then the chords are equidistant from the center of the circle. They are cutting off the same amount of the circle. That means that OM will be congruent to ON. This distance and this distance will be congruent if these two chords are congruent, and vice versa. Okay, so now that we know the theorems about chords and tangents, let's see if we can do some work with these different problems. Okay, so if we have circle O with a radius of 12, chord AB is 8 units from O, what is the length of the chord? All right, let's draw ourselves a picture here. We have a circle with a radius of 12, and chord AB is 8 units from circle for the center O. So that means here is O. I'm going to draw my chord AB here somewhere. It doesn't matter where. Here's my chord AB. Okay, and it's 8 units from O. Now remember, distance is always measured perpendicularly. So if I draw my perpendicular right there, that's got to be perpendicular. It's a radius intersecting a chord. It's got to be perpendicular. And that is 8 units away. So the distance from the center O to the chord is 8 units. It's got to be perpendicular. Okay, now notice I have not put the radius on yet. All right, I'm going to do that now. All right, because I'm looking for the length of the chord. Now remember, this is a radius intersecting a chord. What is it going to do to the chord? It's going to bisect it. So we know that each of these pieces, this one and this one, will be congruent. So if we could figure out what the value of x was, all we'd have to do is double it. All right, now this is where the radius comes in. Does it matter where you draw a radius in a circle? No, it doesn't. So what I'm going to do is I'm going to draw my radius in my circle right here because I can create a right triangle. So my radius right there will be 12. So how would we find x? Pythagorean theorem again. This is a right triangle. So that means that x squared plus 8 squared is equal to 12 squared. So x squared plus 64 equals 144. So subtract the x squared, or 64, x squared will equal 80. And take the square root of both sides. That will be the square root of 80. Oops, 80, not 18. And the square root of 80 is 16 times 5, which is 4 radical 5. So if this is 4 radical 5, and this is 4 radical 5, what is the length of the chord AB? AB will be 8 radical 5. So there we go. Because the radius will bisect the chord because it's perpendicular, you can create a right triangle by drawing in the radius right there. Okay, now what is the degree measure of arc AB? The degree measure of arc AB right there would be equal to the central angle that is intercepted by the chord, is it not? Yeah. All right, so if this is that arc, the central angle would be right here. That would be theta. Okay, now a part of the central angle, but that only goes to here, and it also bisects it. So I can actually draw on the dotted line also right here to make the entire triangle. Okay, if I can figure out this angle, I just have to double it because these would be two congruent triangles. Okay, so let's find the measure of theta. Let's use SOHCAHTOA. Let's use cosine because we know this is 8 and we know this is 12. So the cosine of theta is equal to 8 over 12. All right, since we're looking for the angle, we want to use inverse cosine. Make sure your calculator's in degree mode. So second cos 8 divided by 12, and we get 48 degrees approximately. Oops, 48. So this angle right here is 48 degrees. So that means this angle over here is also 48 degrees. So the measure of arc AB is equal to the measure of angle AOB, and AOB would be 96 degrees. So that is the tangent and the chord, and it intercepts the arc that's created by the central angle there. So that would be 96 degrees. All right, so we've just learned theorems about tangents and chords, and we will be doing the last problem in class together in the next class.